PCB design. So by public demand and changing to the time zone of our live stream, so people from the East Coast and United States can follow through this live stream as well. So I hope you guys are enjoying this time schedule. And so let's dive into it. So let's start talking about what changed. I don't know if you already noted, but we have a different schematic today. Yeah. So yesterday after the live stream, I had some issues with the schematic. Remember that I had to replace the transistors? Yeah, so I started to have a lot of issues with the schematic, and I came to the conclusion that I'm gonna need to make that schematic by myself, like making the components from scratch, and yeah, start over, because when you get those schematics that many people work on them, and I realized that the original schematic from Altium was in imperial units, then it was modified with like metric components, so things weren't connecting properly. And also when I try to replace the transistors, the reference was breaking, like it wasn't identifying the footprints, because we had like that massive lists of libraries and things that weren't using, but they had like similar package names. So it's a mess. Um, so today we have a different amplifier, and this is this amplifier was designed by Dave Erickson, and Dave actually has like a fully completed source measure unit that he developed by himself. And so I took the liberty to get his amplifier design, remake the schematic from scratch. And his design was based on the old Keithley SMUs, so he has some inspiration on the Keithley original design as well. Yeah, and so this amplifier is not as high performance as the amplifier from Hughes that we were routing yesterday, but this is way simpler, and it's higher voltage as well. So this amplifier was designed to go up to 107 volts. So it's a really interesting high voltage amplifier. We know based on his data that this amplifier goes up to 500 kilohertz. So it's pretty good for OSMU, at least for starting. Maybe we were not gonna have the slew rate that we were looking for with the Hughes variant, but it's plenty of bandwidth, at least for us to really have a good start. And the advantage on this design is that it's a proven design. It's already working, was based on a very reliable design from Keithley. So yeah, and it's way simpler, less expensive, so it has its advantage as well. So I just wanna show you guys, like with a little bit more of zoom, what is going on here. I made a library like update, and basically it lost the resistors values, but then afterwards I'm gonna update the schematic with the resistors values. But for us, only matters the resistors powers, and those are all correct, all of them, so the package is correct as well. I checked all the resistors values, so we don't have that problem that we had yesterday, that I didn't know which power rating each one of the resistors. So in the end, we were using like bigger packages than necessary. So this schematic is already like optimized. So as you can see, it's a very straightforward high-speed amplifier. So we have our inputs here. We have our feedback line that on this case is basically made by R14, so very simple design. We have our first transistors here, splitting this signal so we can have our low and high side. So And here we have key 3 and key 8 are our main transistors, bipolar transistors, and then we have those MOSFETs that are basically on a cascode ish topology, and and basically we have a tap here. So if we wanted to switch this amplifier to have a lower voltage rail input rails, we can use those, and we have this last stage here that is for our high voltage over 100 volts. Yeah, I made a few changes as well on the connectors here. Since I already work on the other amplifier on this, I decided to do some optimizations. So the pinout here is a little bit more optimized to use multiple amplifiers on OSMU. And yeah, so for as much flexibility we have on OSMU, it's better because we can test different parts and how they behave in the circuit. So let's go to the PCB. I have some changes here as well. Basically, the PCB format is the same because, as I said, we wanted to test different amplifiers topologies on OSMU. So basically the PCB always is gonna be the same, and the pinout as well. So I have only one change here, that is, let me go to the 3D. As you can see today, I brought the heatsink to the design. So yeah, so I brought the 3D model that I created when we were doing the OSMU mechanical design, conceptual mechanical design. So this is basically a reproduction of the Supermicro heatsink we're going to be using. And as you can see, the board basically fits entirely on this heatsink back, and we're going to leverage it with thermal planes so we can sink as much heat from the transistors we're going to be using. And for this design, we have a different, let's say, methodology, where we, instead of using that tiny SMD transistors and many of them, now we have those big as like D2 pack transistors. And one of the advantages of those transistors, they are very thermally conductive. Their efficiency is really high, and so they have like at least 4 times the heat dissipation compared with the ones that we were using yesterday. Just for you guys to have an idea, those transistors that we were using yesterday from Experience, that package support maximum like 25 watts of heat dissipation. These transistors go over 100 watts of each one of them. Of course, it is in ideal conditions where you can actually sink the heat. But I'm confident that we can come up with a thermal design like to leverage this heat sink. This heat sink is designed for a processor with 145 watts of TDP. So I imagine that is going to be more than enough. This design, it was tested with 1 amp of output current. I believe with these new packages, I had to convert from through-hole transistors to D2 pack. So basically, for the 2 bipolar transistors, I found compatible transistor. Original, they were TIP41 and TIP42C bipolar transistors. So those are the equivalents from on semiconductor for those part numbers with a way better power dissipation capability. So yeah, so I guess it's gonna be easy to go up at least up to 1.5 amps or even 2 amps. Those transistors are limited to 3 amps of continuous current. So yeah, we don't want to stretch to 3 amps because I don't like to go with components in the limits, but like thermally probably it would be possible. Yeah, for 140 watts, yes, absolutely. They would need a massive amount of airflow, but they are 140 watts, but we are not going to operate them. Actually, we're going to operate with less than 50 watts. And the idea is when we want to achieve like more power, we stack those power amplifiers. So this is the reason that I'm using header pins, because we want to stack different amplifiers one on top of each other, so we can have like more heat sinks for each one, or for parts of our power. So we're gonna have a thermal distribution in different heat sinks. Um, and also, initially, we are not going with pre-regulation, but the OSMU future, as like after the prototype version, we wanted to include pre-regulation on before the power amplifier. So this is gonna make our design more efficient, and we're gonna waste way less. Way less power, like only to control our output. So yeah, I think when we get the pre-regulation going, those amplifiers are gonna work pretty chill with this heat sink. Those heat sinks, they have a vapor chamber as well, so they are not like, despite the fact that they look like just a block of aluminum. They are not. They actually have a vapor chamber in the middle, and it's the reason that I always like try to keep the MOSFETs here in this region where the processor is supposed to go, because it's our most efficient region of dissipation. Anyway, so let's start after this long introduction. More than 10 minutes of introduction, it's a lot. So let's start, because yeah, I want to go until we have this thing fully layout, like ready to rock. So key 3 and key 8 are our main transistor output transistors. So we're gonna start with them. And as you can see, we have way less components on this design, so I expect that in a few hours we're gonna have this design fully completed. So for now, I'm gonna just start like by the output here, grabbing the components that are relevant. So R10, R15, R18, R10 should be here. Let's here, R10, R15, and R20, 18, R18 here, R18. So those resistors, I'm keeping them here because since we're gonna parallelize the amplifiers, maybe we're gonna need like some resistors to balance the current between the amplifiers. I think there's a big chance that we're gonna need, since they are like not coupled thermally, and also because I have 3 of them, because we actually have 3 outputs. So one of our ideas for OSMU is to work with a single current measurement range, and for that we're gonna split in different amplifiers in different shunts, so we can have bigger shunts in terms of resistance value, so we have more precision in the current measurement. Because if we went with a single shunt, the shunt would need to be smaller in resistance, and we would lose a precision. We don't know if we were going to be able really to have a satisfactory performance with this design with a single shunt, but it's something that we want to try. So this is the reason that I have 3 different outputs here. And let's say that we have 3 stacked amplifiers here. So I'm gonna solder the specific like resistor here for depending if is the amplifier number 1, 2, or 3. So this is the reason that we have. So basically those resistors, only one is going to be populated on each one of the boards. So first thing that I'm going to do here is to select all those labels. Now we are going to change it to true type font, and I'm going to define as 1 millimeter. So my label, so we can actually can have a reasonable size. And I also, since those resistors are big, let me change this grid that because now I need some accuracy on the positioning. Change my layer to top overlay so I can select my designators. And yeah, and then I'm gonna put an extra text here saying output like MP1, MP2, and MP3. So if people are assembling by hand, they know easily which resistor they needed to populate. Yeah, since the resistors are big, we have this convenience. So those resistors, they're staying here, more or less. Now we are gonna go through and let's see. So now we have R12 and R17. R12, R17, like so. R12 is here. I'm not using the search because there are not many components, so it's just straightforward. So now we have R9 and R19. Let's say if those are easy to find, those are smaller. R19, it's here. Let's see, R9. Yeah, here. Yeah, and then this is just easier to search for them. Clear filter. Then we have R11. Yeah, 11. Okay, so this, yeah, R11 and R16. R11. And R16. I'm gonna follow more or less the same idea to component placement as we had yesterday. So the top of the schematic, that is our high side, it's gonna be on the right, and the low side is gonna be on the left. So I think that is a good organization for the components, and like the traces are gonna align nicely between the input and the output. So this is the reason that I'm following that organization. So then here we have let's see what more we can bring. So to the high side, we can bring key 2 and key 1. I'm not gonna take care too much about position right now because there's way less components on this board. So here we can see that key 1 and key 2, those are our guys. And we're gonna already bring them to this side. So I'm gonna first like position all the components like from the high side on the right side of the board, and now the left side to the low side to the left side. So C1, R1, C1, R1. So those guys go here. This is gonna facilitate a lot. It's just take a little bit to organize the components, but then facilitates a lot. I guess because all of them have like lower numbers. I imagine they are from this side. Yeah, C1, R1, R4. So C3 is the last one. Yeah, R7. Let's see if R7 is this side as well. Yeah, R7 is this guy here, and D2. So all those guys go to the right side. I already know that those big transistors, they go on the low side, so I'm gonna place them on that direction as already. And now we have R8, and then we have here the BEV D3 that I believe is already here. So then we have here Q4. Q4 is basically high side as well. R28. I guess all those other components, Q7. Let's see, Q7. Yeah, Q7 I consider low side as already, and D4 it's your low side. So this row here, let's just bring the components closer, and we are gonna move all this stuff here. Actually, I think my sheet is in the end, so let's just do like so. Like so. Okay, so now we have more or less roughly our components positioned in their respective quadrants, and we can start organize our components. So one thing that I like to do, as you can see, for example, this resistor was on the incorrect side. I already see, you know, that is crossing to the other side, so I'm just gonna organically move it to this side. I just realized that I forgot to put electrolytic capacitors, so I'm gonna need to draw those electrolytic capacitors afterwards because I don't have on this component library. But I just need to keep it to bear then in mind, and keep that I need to add then on the layout afterwards. So it's not a big issue. But yeah, it's just telling you guys if you notice that you are missing electrolytic capacitors. Okay, so as you can see, we have already like some components that are asking to go in this direction. So what we do, we just let them go where they want, basically. Yeah, so like so. Of course, those MOSFETs, they go in the middle, but yeah, I'm just organizing right now, so we can have a clear view of where those components go. Yeah, those are our range. As you can see here, I have those R3 and R5 that they are between medium voltage and low voltage. Because I define it here in the connector that we're going to have a low voltage rail, a middle voltage rail, and a high voltage rail. And then maybe we are going to add new sections here on this amplifier. But for now, we're going to test with resistors here, so I can select. So the selection resistors are R3 and R5 and R26 and R28. So it makes sense why these resistors went to go here, is because they are our selection resistors as well. As you can see, this one goes here. Okay, that's all right. We have a lot of space on this board. Usually, I take more time to do like boards that has a lot of space, because there are so many options and ways. When you have a very tight board that you need to lay out like carefully, I don't know. I just have this thing that I think looks like it's easier when you have a Okay, so this guys goes here because those smaller transistors, they are those guys, key 7 and Q4. Yeah, and then after then we have the Q5 and Q6, and those are SOT23. So Q5, Q6 is here. So these transistors go here, and Q5 it goes here. I basically have mentalized the schematic. I did this schematic this morning, so I more or less know where things should go. And this is the reason when you do the schematic and the PCB at once, you just keep in your mind. Okay, so here we have R13 and R14. Those define our gain, our amplifier gain. R13 and what was that? Yeah, R14. Let's find R14. I think it's the other side. R14. Okay. So those guys, they are naturally gonna be here on our input. So this guy definitely goes here, and this guy comes from our feedback line. Here probably I'm gonna, yeah, this line here is our feedback line. So this is very important, and yeah, I need to take a lot of care to write this line. Anyway, let's move forward. Now let's come back to D3 and Q5. Okay, so let's find G3. Okay, so this G3 goes more or less here. G2. Okay, this G2 goes close to Q2. So this one. So let's keep it then close. Okay, so we have D7 and D8, and they go in close to the output. Where is our SOT diodes? Okay, so D7. So let's find D7. Okay, D7 and D8. Clear filter. So those guys, they would go more or less around here. Looks a mess, but it's a mess under control. So okay, D1 goes close to Q1. Very convenient when they have similar names. And then we have here R4, R2, R4 and R2. Okay, so R2 goes close to the Q1 because it goes to the base. So our Q1 here. R4 goes between Q1 and Q2. And R6 goes to the gate, yeah, the gate of Q2. It's not base, it's R6. Yeah. Then we have here C3. C3 goes in parallel with R8. Oh, they are conveniently close together. Thank you, Altium. And they go, okay, so they go between our output line that basically shares everything here and R6 and C2. R6 and R6 is here. Where is C2? Okay. Those guys, let's keep them around here for now. Okay, so now that we have our first roughing in terms of component positioning, we go to the low side, and basically we're going to do the same, but starting from the opposite side. So So first we have Q10. So Q10. So this guy goes around here. This guy goes around here. Then we have C6R30. So let's find here C6 and R30. They are close together. So let's grab clear filter. So they go more or less on this side. Here is our voltage rails input. So let's consider they're going to stay around there. Then we have R29. R29. And it goes to the gate of Q10. So this guy goes more or less here. Then we have our first diode is D6. This 6 is Shift C. Yeah, okay. I need to learn this shortcut. D6. Naturally, D5 goes here. Yeah, D5 goes on Q9. Then we have here C5 and R27. R27. So this connects both of them. And where is our C5? It's here. Beautiful. And yeah, we could make this board way smaller, but because I need to rely on the heatsink mounting points, and then it's gonna be the same size. But yeah, we could make like with 50% of the other board size with slack. Then we have like R24. I think I already placed around there. R24, no, but this guy goes here. And then we have C4 in R21. So C4 and R21. These guys, they go more or less here for now. D4, okay, D4 goes close to Q6. Q6, where is Q6? It's easy, it's just follow the money or follow the net list. Then we have this R22. Okay, so R22, it goes on our voltage rail here, R minus 15. And we have 3 guys here that are, where I'm missing you guys. Okay, so I have R23. Let's see where R23 goes. 21, 24, it's very close. Okay, so there are some feedback. 20, 23, and 25. 20, 23, and 25. Those, they go in a feedback line here. That is actually optional. But they are not option for the Hughes amplifier. So yeah, so we need to keep a standard, and this is the reason. They are basically gonna be zero ohms resistors. And I actually, no, I'm gonna keep it this way. It's all right. There's a reason for the pinout connections. Okay, so we have our rough positioning. Very ugly, but as you can see, we have plenty. Reset error markers. The error is because the heatsink is slightly bigger than the board, and auto just crash. Yeah, so as you can see, we're gonna have plenty of space for this amplifier design. So let's start bringing the symmetry that we all are looking forward for. now that we did like the first roughing component placement, now I like to optimize, and this phase it takes a little bit longer, but because we are like more or less positioned most of things, now it's more about routing strategy. First is more like, oh, let's tidy the house, you know, and now we need to think in a strategic way, because yeah, we have things to route, and they needed to be routed accordingly. Um, so first of all, so those are our two main output transistors, and they should be as closer as possible with our output header pins. So we're gonna be bringing them. I just need to check here what is the output. So it's pin number. Okay, so we have actually R17 and R12, so they are not connected directly. But yeah, it's pin 4. So basically the tab, our tab is our output, and well, makes a lot of sense. So, and this is very convenient as well, because we can keep it then. It's not exactly convenient, because yeah, there is one issue. If you do like this, you're concentrating the heat on a smaller region, so it's less thermally efficient. So what I'm gonna try to do here is to work on this design, and then I don't have a clear vision yet how I would like to have, but you see this FBR here is feedback return. So basically this is our main output, and this is where all our power is gonna be fed on. So those resistors, the R17 and the R12, despite the fact that they are only 1 watt resistors, they are only 1 watt because they are very low resistance. I think, if I remember correctly, they are 25 R. So they have a considerable amount of power going through them. So they should stay here in our cooling zone. So we keep them with a lower temperature as well. And then those resistors, they are basically doing biasing, so you can see that they are only half a watt resistors. They could be even lower, but I decided to have a slightly bigger resistor, so they are half watt, because yeah, we have a lot of free space, you know. So free space, you can use components that are slightly bigger. So yeah, when we are prototyping, it's just easier to place with your tweezers, the components, yeah. So just convenience. Then we have Q5 and Q6, and okay, so then we have R11 and R. I think those resistors, yeah, they should be more or less on this line. And yeah, I actually thinking now straight, because yeah, what's gonna happen is basically this, right? And if I keep like putting a lot of resistors on the region, I'm not gonna have all the clearance that I want to have. The reason for it, because we have like but bigger transistors, but less count of them, I want to optimize thermal vias around the transistors. So if I keep this region too tight, like we did with the other amplifier because of our space constraints, then I am gonna have less space to make some vias stitching here, you know, because I'm gonna have vias like under the MOSFETs. Because usually you want to avoid vias under the MOSFETs, because they tend to sink all the solder from them, and this could cause like equality issues on the solder. So in a manufacturing standpoint of view, you usually don't wanna vias under your MOSFETs, but on our case it's critical. So we must have vias there because it's the main source of power, and we want to, in a worst case scenario, dissipate a lot of heat. So for this the reason we're gonna have vias under the MOSFET, but I also want to have around the MOSFET extra vias. So I need to have space because we're gonna have like a power plane, a thermal plane under those transistors pads. So for this reason, I'm gonna move those resistors here a little bit lower, and actually those transistors, I'm gonna move them borderline here. It's like on the heatsink that we're gonna use. This region is yet yet like a vapor chamber, but like the official specification from Intel for the LGA 2011 is this 38 millimeters here that we have. So so what I want to do is do like so, and I'm actually gonna invert them, because then we have like more spreading of heat on our PCB, and we have less heat accumulated in the middle. So I think I'm gonna follow this strategy through the entire board. And I already see that this is our MOSFET that goes on the other end of the low side. So we're gonna keep this MOSFET around here. So let's take out of our region of interest all of those small components. And now we bring this guy like so, and this guy like so. And as you can see, now we basically have like almost perfect region to spread our heat from those 6 big MOSFETs that are our main source of heat through the most efficient region of our heatsink. So it's starting to look good to me. So let's move forward. There's a lot of things crossing right now here. So we're gonna address this soon. I'm just like starting to mentalize, everything that is crossing, and to find the common place for them. On the case of those MOSFETs, yeah, it's kind of not optimal to keep the tabs outside. We would need to do a slightly different strategy here. We are going with a 4-layer board strategy. So what I can do to optimize thermal dissipation is to keep I'm gonna keep here our layer 2, that is the middle bottom layer, as a single. Yeah, no, I think I have an idea how to do it. Since this amplifier is way simpler than the other one, yeah. So for each one of those pads, I'm gonna create very big thermal planes under it, because yeah, they are in different potentials. So I can't just create like a single thermal plane in the back, because I would short the entire amplifier. So I'm gonna create like thermal strips here, and we're gonna have basically Between the heat sink, as you can see, there's a gap here. So we're going to have a conductive pad, but it's an electrical isolator as well. So this pad is going to cover the entire heat sink. So what I'm going to create strips from going from the transistor tab to the side for each one of those transistors, so we can conduct well. And also I'm going to create those strips. Yeah. Uh, yeah, it's okay. I know what I need to do. It's actually, I was not thinking as I should, because actually those small pads, they don't need to stay here in the middle. The reason for that is because our big pads here is the guy who actually is gonna conduct the heat. Those small pads here, they are not like they are bond wired connections with the silicon, so they are not big responsible for to remove our heat. So it's gonna be way smarter if we just give the proper space for our transistors and we actually move the legs outside of our region of interest. The reason for that is because it's gonna facilitate a lot the layout, because see like what happens now. You see this diode. Now we basically do this and we are basically done, you know. So I always think about like a strategy that allows you to short your paths between the components. So this facilitates a lot the design and makes brings more performance to your circuit. Because imagine this is an amplifier that has relatively high frequency through the power that we are seeking for. So we reduce inductance and capacitance if we shorten our traces, and this is gonna increase, even if it's slightly, the amplifier performance. So why not just think a little bit more on your design and you're gonna be good to go. Okay, so now we started to see a pattern here, right, where the components want to go, because yeah, it's very easy to rotate. I think rotating a board is very easy. You just need to, it's like driving a car, you know. Just follow the GPS, and usually the GPS route is the best one, because yeah, there's a lot in consideration there. You know, lane speed and traffic, and the net. And this is the beauty of having a net list, accurate net list from your schematic, because you can visualize where your net lists are asking to go in your design. So this facilitates a lot our life. So as you can see, that things like just start, you know, to uh, to fit in the design. And as you can see, we start to come up with a design where things don't cross anymore. So you start to see where it should go when your components, they stop to cross between each other. Now we can see that those components, they are calling this one as well, as you see. So it's organically, it starts to ask, oh, I want to go here. So R11, R9, let me see what those guys are, why they are asking to go on that direction. Let me see. R11. Oh, okay, so they're biasing for Q5. So those guys, they could stay like around here for now. And Q5, those small transistors, they can stay around here. Some paths are a little bit. Can I find some more information about OSMU project? Absolutely. I'm gonna give you the link. It's wiki.osmu.dev. And we have a forum as well, but we are on Discord. I can't. It basically the discussion the mainly discussion happens on Marco Rep's Discord server. I can't just give you publicly an invitation if you are not there yet, but I can give you an invitation to my server, and then I can give you then the invitation for our main OSMU groups and channels. Sorry, and the extra references. So we are very active on Discord regarding OSMU. We have an old forum. It's forum.osmu.dev as well. And we also have our Git, that is git.osmu.dev. The forum we are basically not using because everything happens on Discord nowadays, so we basically abandoned the forum. But there is some interesting old discussions there, like from 6-8 months ago, when we heavily started discussing different parts of OSMU. So if you want to like in some history about OSMU, you're gonna find on the forum. Anyway, let's continue. There's so much space. I just get totally lost when I am so comfortable to to lay out a board like this. Yeah. So 6 and R30. So yeah, I know who those guys are. They are our match from the R1 from the other side. So here we started doing the same process, looking where the components want to go. Okay, so I want to be around here, Vini. So and those guys, they want to be, you see, around here. Okay. All right. Let me see. FBR, and this is okay. And this guy, it wants to go like so. So maybe let's leave him where he wants to go. So R9, R11, and they have like a pair that is R16 and R19. R16. Okay, so those guys. Since now with this new strategy, we do have space. So what I could do is No. Mm. Okay, I'm gonna commit with this. So I'm gonna put this resistor at 4 millimeters, and this one is gonna be less 4, and we're gonna lock those resistors. Gonna lock because it needs to start committing, and we're gonna do like oh, I need to actually define my design rules. Uh, uh, Less for this project, we don't need less than 0.4, preferred width 1 millimeter, and max, I don't know, 10. It's a very rough clearance. Yeah, so I went like 0.3. I also want to make this board like compliant, so expansion always 0, because then the manufacturer can define paste mask. This we're not gonna change. Maybe I'm gonna optimize this afterwards. Hole size, so minimum hole size 0.4, maximum 10. Minimal solder masks. This is okay. This I don't care as well. Board outline clearance always creates a roll, and this usually is 0.3 millimeters from most of the manufacturers. Okay, so 0.2 vertical clearance and horizontal clearance. Yeah, this is more like a manufacturing thing, so 0.2 is usually what I like. And hi guys, call me Luke. Yeah, this is Altium designer. Uh, this is a professional EDA. And we are using only Altium Design right now because we decided that in the prototype phase we're gonna be using the EDA that we are most comfortable with, and for most of the guys that are actually developing boards, we were more comfortable with Altium. So to gain speed, we are using Altium. When we decide, oh, now we have a stable design, then we are gonna ask you from all the collaborators, oh, now we need to port to KiCad this design, because OSMU, as the name says, open source measurement unit, so everything must be open source and the EDA. So for in the beginning, we're gonna keep the main design files on Altium so we can prototype faster. When we come up with like the version 1, and then you're gonna have schematics and everything on KiCad. That's the idea. Routing via style, routing vias. Okay, so vias is important. And I think we don't need vias less than 0.4. Maximum, I don't know, 2 millimeters. Prefer it. I think like 0.5 is usually a size that I like. So minimum 0.4. So we need at least a diameter of 0.65. It's just trying to bring it by heart. So 3. And if my preferred is, so it's gonna be like 0.8. Do I have anything else for now? I think this is the base. So as you can see, those resistors, they started to ask where I want to go. And since the FBR is on this region, we're gonna go like so. Yeah, let's bring the silk screen here, because then we can, yeah, we have a lot of space. I am just like very perfectionist. I like to keep things very tidy. Yeah, so like so. As you can see here in the middle, I'm keeping our, I usually like to keep even like that. This would be more symmetric if we wanted to have a symmetry line. Usually for the silk screen, I like to keep in only one direction, because when you are actually working on the board, is just easier. How is the progress so far, guys? What do you think? Do you think we're gonna finish this evening? I'm optimistic that we can finish. Those diodes, they are kind of important, and they are here in the output. So they're gonna stay like so. In the case of those diodes, I have plenty of space. Those go in the middle. Okay, so let's define 3.5. So 3.5 minus 26. We have plenty of space, so we don't need to tie them. Okay, and we can lock those components as well. They are in a very nice, and you see, symmetrical position, so we keep them there. And those resistors, actually, we can, I don't know, but I'm gonna cook dinner at some point. Probably won't have time to watch the whole thing. It's all right. What is your name? PMC. Okay, so let's call you Paul. uh, it's all right, so stay as much as you want. If you want to come back after your dinner, I'm gonna be happy with your presence here. So yeah, so this resistor, as you can see, it is not aligned, and I'm gonna align him. And here I'm gonna put like 4 millimeters. This is only one is gonna be populated. So I don't mind, oops, -4. I don't mind so much that they, and those resistors we can already like wrote them. So, nope, not bottom, top layer. So here we can use, I think, 1.2, no, much more, 1.5, no, 2. Yeah, we can use the TLC2. And we can do the same here. Then afterwards, I optimize those. It's very straightforward to change track sizes on Altium. So yeah, so we have our first trace. They're not symmetrical, but there's no way on this case to make them symmetric. Those could be very high voltage. So as you can see, I have some not populated pin headers here. So because here we have some grounds to provide some shielding, and then I kept, because this can go like up like 350 volts peak to peak. So yeah, it would be too small clearance, you know. So probably I'm not gonna even solder any pins here. And I'm not gonna remove the pads from here. because then people need to actually cut you know, the header pins and just make it messier. At some point it would be good actually, because as you can see, the connectors, they have asymmetry, so people could twist the board and connect the input and the output, and that would be like very bad. So actually, if we remove those vias, and I can do this easily, we would make the circuit safer and people could not screw up. So I'm gonna do this right now since I had this idea. And now I have everything on. Oh no, wait, I can't do this as easily. No, I'm gonna do this later because I'm using the same footprint for the two connectors. So I'm gonna need to separate different footprints so I can do this indexing. But yeah, this is definitely something that I'm gonna do. So I'm gonna remove the pads 17, 18, and 25 and 26. We're gonna have more clearance here. I can also make some board cutouts here, so we can make our high voltage traces very separate, and we can avoid leakage in the board, because we're really talking, this amplifier, it is really high voltage, so we need to take care about leakage on this model. The other amplifier that we were working was like 60 volts peak to peak, so way lower issue in terms of board PCB leakage, but on this case we need to take a lot of care of it. Anyways, let's continue. Now here I'm gonna kind of connect a big S trace for now. Let's call this 4 millimeters. But don't expect, as you can see now, and this is the reason that I starting doing like so. Now we can bring this guy like so, and like, yeah, better if we do like so, because then we keep it the same. We keep it the same distance. This is just an idea for now. Probably I'm gonna change afterwards. And I actually, since they would be misaligned, would make sense to bring those resistors on this direction. So okay, so our silk is on this side. This is a very organic process, and I'm always changing my mind. And PCB is something that is very important when you are making your layout. Never commit too early with some routing, because don't get attached with it, because when you realize, you're gonna see that, oh no, this is not ideal, but oh, now I already wrote like 25% of more boards, but then you come up with a realization that, oh, if you had moved it in another way, it would be way better, you know, your layouts. Don't feel sorry to go there and delete all your routing and start over, because it's the difference from a good to an excellent layout. So here is the case where we actually can start thinking about our to have a power plane, and I'm pretty much sure that I'm gonna do this. I'm gonna bring those resistors like a little bit far away. Like so. Let's look into how it's looking like for now. Yeah, looks great. So here we have our first region of where we can create a polygon. So we basically can do. I can move the polygon points afterwards, but now we need to define that our net is the net Q34. So net Q34. And here in the configuration we say remove dead copper because I don't want dead copper. And we can commit with the layout. Now I'm gonna need to, so why didn't you connect it? It did not recognize. So I can use the probe here and say connect to this one, and then I can go to polygon actions, report all. So you see that this is something that I let for you guys to see afterwards. Here is a conflict between what is optimal for manufacturing and what is optimal for the design. Since we want to maximize heat transfer, this how does this call it? Let me see here on the rules. I just forgot. So the plane connect, this relief is the name. This is very good for manufacturing. The reason is because when you have this big thermal mass here, what is gonna happen is this pad here, it's gonna heat up first and melt the solder first in the reflow oven. And when you have one pad like melting first, what this solder does? It drags the component. And usually what happens with these small resistors is that the resistor do and basically so you get like a resistor like a spire, so this causes a lot of like soldering errors. So this is the reason that relief was invented, because you are reducing the thermal conductivity between your solder and the pad itself, so they more or less melt at the same time, and this way the solder grabs the component, aligns it. So you have less manufacturing issues when you are automating your component soldering. But in your case here, for this resistor would be totally fine. For the transistor, it's a no-go. Why? Because we want to extract this heat here. So we don't want to have this cutout on the transistor. So on Altium, what we are gonna need to do is define a specific rule. So we're gonna need, so you can see that we have here the plane connect and polygon connect. So what we need to do is create a rule where this component matches, you see net class. So no net. So here, so no, I have an easier way to do. That is, it's custom query, and then in component, but it's like opposite in components, and then we have here Q3. I don't remember the Altium syntax. I don't know if it accepts this. Yes, I wanted to correct it then. Let me see if I can do like inverted. No, I don't don't know. Yeah, so it's just because I don't know how to invert. And hey, ways, uh, pretty good. So ways use Altium as well. How can I invert the logic? Like in programming, like we use like the exclamation mark. So I want to say, oh, in all on other components, because other way I'm gonna create a different rule and say, oh, no relief connect if is this component. If you know by heart, so let's define this as all. Then we're gonna create here a new rule. So this is the way that I'm gonna use. And this priority, so no, let's call it no relief. Okay, so in no relief we're gonna no oops direct connection, and via connection direct connect. Okay, and then we're gonna define here custom query. So in component Q3 and, or maybe and in component. Okay, so let's just define Q3 for now, because I just wanted to explain you guys how. But let me get to yeah. Please, I don't usually use this custom queries so often, but yeah. So since we are here, I'm trying to teach the guys. So yeah. So now we can go in polygonal actions, report all. Oh wait, no, rules. I define it for power plane, but I need to define it as polygonal connect as well. So new rule. So no relief. No. Let's call no relief poly. The rules can't be the same name. Then we define direct connect. So we can actually call it simple here. And custom query in component Q3. And this is the magic on Altium, because I don't think KiCad has any capability like this yet. Well, I don't use KiCad. I'm just it's like saying without spaces, but yeah, I'm not sure if KiCad already has like this advancing like configurations for nets. And so report all, and ta-da! So now we have our transistor that needs the thermal pad connected, and we have our resistors that do not want to have a big ass thermal mass with a relief connection. So perfect. And now we can move on, and afterwards I can put on the query all the remaining transistors. I just want to show you guys one, but this usually you can do this after you finish the layout. It's more like optimizations on your design. I'm happy that it worked as I was expecting. And so now we can move forward. This trace here, probably I'm gonna create a polygon as well, because here we also have the same issue. You know, we are creating a big trace. It's not as bad as a power plane usually, or a polygon plane. But yeah, it can cause some issues. So probably I'm gonna replace this, but for now I just wanna have like a reference. So because this way our components that must connect, so for example the feedback line here, it's already gonna ask for, oh, I want to be connected here because it's the closest place. So start like creating those traces. Even if you decided to delete afterwards, it helps a lot you to speed up things on your layout. And as you can see here, we already see that we have a cross here. Why? Because Q5 wants to connect on this side because we have a crossing. So as you can see here, the low side, we have a low side here, but also the Q7 connects to our high side 15 volts. So we have this crossing here. So now we need to decide where we want to keep those connections, you know. So we keep this transistor really in the low side of our PCB, or we move to the high side and then we route the remaining connections. So first, the base, we have a neutral connection, because yeah, this is our division line. All right, this is our division line. So this is neutral because it connects to our feedback, and this connects to our low side. So, and this connects to our low side, and here we have this single high side. So since we have 4 layers, what we are gonna do is we're gonna use the middle top layer as our minus 15 and plus 15. So on this case, I don't care about this 15 right now, because it's gonna be connected to our middle layer. So Q7, it's gonna stay on the low side. So as you can see here, our Q7 is staying on the low side, but we have Q6 as well. And Q6, on this case, it wants to connect to the low side and through this diode as well to the low side. So Q6 is definitely gonna stay on the low side. And so like so. And this connection, why this connection is asking? D4, R16 and R19. They should be R16 and R19. This is key Q8. Q8 is the low side. Okay, so I found a mistake here. So this guy should be in the opposite direction. So what we're gonna do here right now is say, my bad, you go this side, and Q8 goes on this side. Because those lines were crossing and they shouldn't cross based on what our schematic says. So we're just gonna fix them. Yeah, and now so now that the commitment that I did here, it's gonna change. Let's just unblock those components first. That's okay. So this one, it becomes, wait, I unblocked you, I guess I did. And I also unblocked this guy, Altium. So this guy goes here, and now this guy goes here. You see, just what was the query solution to the relief? Yeah, so what I did, I create because I didn't know how to invert, I created an additional no relief rule, and I defined in component like this one, but now I need end, so probably I'm gonna need, so let's check and already fix this. So I have like Q3. I don't know if I can like just change lines, or I need to define an end, and or on Q3, or let me fix my keyboard, US keyboard, or in component, let's try Q1. Let's see if Altium accepts this. Yeah, it's accept. So or it's working, or so or in component Q2, and then we have on this side or in component Q8 or in component Q9 or in component. I could define a component class, but yeah, this is just easier. Okay, and now we're just gonna copy this. So we apply here, and the power plane, we also define here that those transistors, they are special case, and they don't ask for relief. They're gonna be stressed, the transistors. Okay, so this transistor here, as you can see, it should go here in the middle. This transistor also is already in the middle, and so on this case, I'm gonna define here, so 15 minus 15.5, so 15.5. Alright, so those I'm pretty sure that they're not gonna change anymore. I hope. Let me see. Q9, yeah, Q9 and Q10. They are correctly on their positions. And now we can define this as, okay, so let's try 13. Yeah, 13, perfect. And this is minus 13. And minus 15.5. 13. Okay, so these are on their correct position now. And now we can define this as and this what was I just forgot. Okay, minus 13. Yeah, so minus 13, perfect. This is correct. Alright, and 13 and 13 and a half, 15 and a half. Okay, so now we lock them as well. The query solution. Probably you already got it, but just for recording purpose. So let's fix those resistors right now. So minus 5. Uh, 5. Position minus 22. Minus 22. Yeah, I'm pretty sure now that we are not gonna have this issue anymore. I just need to fix their silk screen. Let's just look the board so far. Looking good. Yeah, so now I love the fact when Altium started to lose. It's, look, dude, you have a track here. Why you were trying to to give me an at least far away, you know? Okay, so like so. That symmetry, yeah. Oh, yes. So, symmetry freak. This is me. Like so. Uh, all right. So, here I have this opportunity because as you can see, yeah, we definitely should go. Yeah, I was thinking after I finished this design, I was actually thinking to make a wireframe, you know, with the 3D of this board and actually make a T-shirt. It was on my mind already. Yeah. Okay. Okay. So this guy and this guy, they go like so, because then we bring this guy like so. And now is the moment that we start having some inverted. You see what I'm doing here? Let's lock those guys around here. And oops. No, there. Please respect me, Altium. I know you can. Okay, I'm gonna give you some slack. The traces are impossible to see to be symmetric, but then you just make like a matte black board, you know, and no one's gonna see the traces. So, despite the fact that I like to make my traces symmetric as well, this is not always the case, and this is one of those cases. And as you can see, now we started to bring the traces out. I'm not gonna rotate them, but yeah, you already see that where this is going. So this diode, well, we can rotate them because yeah, doesn't. Now is the case. This is what makes most sense, right? You keep there. Okay, so here not so close. It says let me check something. Is it in no? Oops, where's my this is very overkill what I'm doing here right now. Rounding, positioning, and but hey, if you're not perfectionist, what you are doing on this live stream? And one of the cool features about Altium is like you can do this. Yeah. And you can come up here and do like this. And now I'm a happy Pokemon with more symmetry. And since we are here, we can just say, well, we have plenty of space, so I'm gonna give some slack to this. So minus 28, minus 28, and here 2.5. Now you are locked. And here I can say 1.5 millimeter. Yeah. 2. Yeah. Yeah. For now, let's keep it this way. Ugly, not symmetric trace. But it's passable. Okay, so those guys, I want to keep them in the same alignment as, let me remember those, so 4125. Oh, why? Oh, it's right. minus 22 minus 14. 14 on 5. Nope, completely forgot again. 41.25. I know I could be using the alignment tools on Altium. I know, but so let's lock those boys. And now we can actually I'm changing my mind because this is stupid and I should be ashamed of it. And you guys gonna know later why I'm doing this change. If you're smart, you're gonna know why I'm doing this change. Okay, so now here we can define that let's define this trace with like 3 millimeters. So we can basically grab all of them. And here we can do basically the same. And we get all of them. Of course, if you wanna be, oh no, I wanna create like a polygon here to fit nicely, it's up to you. Why there is so much difference? Oh, wait. Two of my boys are yeah, no, that's not gonna work. I'm not gonna be happy. So here we're gonna create a fucking polygon. So that's gonna fit like so. Let's do a proper job. I know you are. Minus LV. Altium, please, just be compliant. You see? And here we can have our relief. Okay, let's create other one here because you guys, I know you guys are exactly like me, fucking perfectionists, and you're gonna keep me telling me for the rest of my life that I didn't did this properly. Shame on you. Okay. Okay, so what I was going to do is, where is my beautiful, no, it's there. So what we are gonna do here is we're gonna define a board cutout. And this board cutout. So we can start outside. And then we're gonna say, okay, I want to have some clearance between those components. Hey, and now it's gonna complain because it's less than 0.3, but I'm almost pretty sure that the manufacturer lets us do this. Yeah, so for now I'm gonna leave this, and then if they complain, I just needed to define this. Yeah, no, it's on the limit. Yeah, because here we have our high voltage, and despite the fact that we have a progressive voltage here, like this high voltage is like almost 200 volts. And this middle voltage here, it's not defined how much it's gonna be yet. So it's good to keep this thing like so, and then we actually can copy this thing, and then we can define okay, so we're gonna actually here we're gonna have a cutout afterwards, but I'm gonna remove first and here we can have our second cutout. Oh, look what a beautiful cutout. Always avoid your leakages when you can. Now here we don't need Let's drink some water because my voice is fading away. And let's create that polygon that I had to delete before. And since we have our rule working, we have our relief correctly created. And look what I can do now. I can say create here because we have identical. And we have an identical symmetric polygonal plane. Look, what a beautiful design. 5 viewers. Say something, guys. Otherwise, people are gonna think I'm crazy that I'm talking alone. I'm kind of crazy, but I guess on a reasonable level of craziness. And we can bring a little bit of clearance here. It's not really necessary, but this is more or less. Hey, thank you very much for your support. I'm really enjoying this live stream thing. It's like my, I think, third live stream, but yeah, it's so much easier, because I can share things with you guys, and like giving some teaching. I'm not usually. I'm laughing in the background. Yeah, so I can share like some tips and tricks. I am not like a PCB designer professional, but I already made a lot of PCBs for myself, like for many years. So I I consider myself reasonable good at it. So yeah, I can give you general tips and tricks and things that I know what I'm doing, and like inspires me because when I need to do a video, and there's a reason that have been very like away from YouTube, is that like takes a lot of time, you know. I'm very perfectionist, so I need to have the sound right, I need to have the camera right, the lights, I need to write a script. And when I'm making the videos that I like to speak, like when I'm talking like in the live stream, I really don't care that my English is not 100% perfect. But like when I'm making the videos, I like to maybe my scripts to be as perfect as possible. So it takes a lot of time. So in the end, I get like not motivated, you know, to make official videos. So this live stream for me works much better because I can produce a lot of more things and I can bring more value to my viewers. I know that this like is just like I don't know. I didn't check like the analytics for the live streams, but I know that's much less people that are viewing this than that usually I would have with a normal video. But yeah, I like this dynamic. So for now, I'm keeping this way. Anyways, let's see what we have here right now. Okay, so we have minus high voltage. Okay, so we have more FBR. So those could go there in the middle, like those two. Let me just check them. So 1916. So we had here 1916. Then those that are asking for are C4 and R21. So here, C4, R21, they are connected to our output line. So we have, yes, we can put them in the middle. They are basically in parallel. And then we have this R24 resistors that goes to the gate of Q9 and connects to D5. So we're gonna be working on this region here right now. C4, R21, R24, and D5. So D5 should be close there as well, yeah. So D5, then we have R24, that is our gate resistor. And then we have R, and then, oops, just forgot it, R, C4 and R21. C4, R21. And so on this case, so now we have a change here. The reason is because now we have a connection that needs to go through this path with this, and this is relatively no, not always. It's just on this specific case because we have a very symmetric schematic like in amplifiers. So on this case, when it's possible and when the schematic is very symmetric, then I like to align. But usually, if it's like more like frequency critical, I'm gonna go in the road where the traces are shorter as possible. But I always take in consideration, for example, power lines. So if I have like critical power lines, then I'm gonna make a design like focused on like power handling. Um, so yeah, it depends the kind of circuit designing. So if it's a small signal, high frequency, usually just gonna be shorted um, traces as possible. If it's like more a power design, then I'm gonna focus in thermals and current handling between the trace. So yeah, it varies a lot. I probably am gonna do more of those boards, and then we can come back also to the OSMU control model that has a totally different strategy because yeah, it's small signal, like focusing more like noise suppression, and then there we're gonna have a totally different strategy than I have here right now. And there's no much symmetry because all the components are all over the place, like very different components. So yeah, so we only have like the differential pairs that they're gonna be symmetric, the remainder of stuff. So yeah, then I don't bother. But when it's like a design like this that can like leverage a very nice and beautiful design, yeah, look how it's already starting to look. You know, it's it's just gorgeous. It just makes everyone happier. So okay, so on this case, first of all, I'm gonna create a new polygon here. Right. And yeah, so this polygon, I can bring it up to the middle here, and then gonna make it like so. It's all right. Now we can start optimizing a little bit because yeah, I don't need all this, and I could stretch a little bit on this side. I kinda don't like this, so I guess this is the way. Yeah, looks better. Now on this side is not gonna be symmetric, so yeah, that is all right. I'm not gonna be like as proud as would like to. And close your eyes, guys. But what we are gonna do is to bring And now we're gonna optimize this. Like so. Yeah, here is a big advantage too. Yeah, and here actually doesn't need to go that far. Okay. One last problem. And now this tab has a lot of region here, so I can create this. Yeah, so this goes directly here to the input, you know. So, and of course here in the sites, this is space that I'm leaving here. It's where I'm gonna put the electrolytic capacitors afterwards that I forgot. Anyway, okay, so now that we solved this the disconnections that were important, this already creates some restrictions to me, and this is the reason that I wanted to create it, because on this case here I had this plenty of this space to come up with a trace here from the middle, so I could keep those Q6 and Q5 transistors here in the middle. Now it's the way I like it. But on this case here, we're gonna need to go from the side. So for this reason, QR, those guys, they are gonna go here, I think. And since we are working on those guys, I'm already gonna grab their pairs. So C3 and R8, and I'm gonna bring more or less then in the same place, because we already know that. Yeah, and you see that things started to align automatically when we take the right route. So as you can see that though this guy can go to 0, and I guess it can go like 30 as well. If even, yeah, even like 28, 25, no, 26, yeah, here I like it here, around here. So now we can, let's see if, welcome. Okay, welcome people to Discord. I'm just checking Discord. So now we can say that this guy goes like so. Big trace. This guy can go like so. You as well. pretty much lock it with this resistor. I think this one, oh, I already locked it, so it's all right. This is just small signal, so but since we have so much room on this board, we can just say, oh, this 1 millimeter. Thick trace is rare when I have all this space for so thick traces. Now those guys. Okay, so minus 15, but it's asking to go on this side. Since I'm gonna have a minus plane on this side, I'm gonna move this guy here, and I'm gonna move this guy here. Because this, in terms of on a thermal management point of view, it's gonna make more sense to me. Why is the larger center trace off center? You mean this one? Yeah, you are completely right, like so. No. Yeah, don't worry. This trace, I'm gonna replace this large center with a polygon as well. I'm just keeping here, you know, for, as I said in the beginning, so I have a reference. But yeah, I'm probably gonna pour a big polygon. I just wanna keep things tidy. Okay, so now we have something that we need to account for. And I'm gonna explain routing a temporary route. So just let me move those stuff from my way, because now we have this situation. So let's define here, like what is the maximum I can go. Yeah, just make it big. So this is like it's not gonna be big like this, because this is high voltage, low current. But I just wanna exemplify, right? So this big trace is important because this comes from our main rail and must be connected in a way, and like those components, so those components, they must be closer to the gates. And here I have like a small trace, you know, to bring some biasing to those components probably. So yeah, they are important, but they are not as important as our power trace. So what I'm gonna do is those traces I'm gonna move to the middle or to the bottom layer, and then we route them in a second layer. So this is the moment that we start thinking in a multi-layer. As you can see, basically we wrote everything until now in a single layer. So this board actually could be, in terms of complexity, made like very easily in 2 layers. But since we want to have the thermal planes, and also I want to have some shielding between, you know, the signals, then we are going with 4 layers. But would be possible to make with 2 layers this board. You would only need to adjust a few things here and there. But yeah. And we also have, now let's unroute nets, and we define this net. Yes, and as a magic, our trace vanishes. And so now we have actually this one, and this is important. And this we can move this to 4 millimeters. We don't need more than 4 millimeters. and this is gonna connect like so. This trace doesn't need to be as thick like this, so afterwards I'm gonna work on the clearance. For now I'm just making like a rough, and maybe I'm gonna convert this to a. So here now we move to something sane, like 3 millimeters. Yeah, we need. I just wanna wrote something sane so you guys have a reference of our power lines, and for me it's a good reference as well. So here we have our high voltage positive, and the same thing is gonna happen here, where we grab our high voltage like so. Well, I had defined it 4 millimeters in the other one. Yeah, like so. This is gonna change afterwards when I place the capacitors, but I just wanna give you guys a sense of. Yeah, actually those fiducials, they're annoying me. Probably I'm gonna move them because they don't need to be there, and I'm just making my traces less perfect. So like so. Guys, I come back in 2 minutes. I need to do some pee. I'm back. So let's go. I can fix this. That's bad. Not an issue. This is gonna be. It's gonna become a. Oh, I forgot to create the planes here. So let's do it. Just doesn't look right to me. Oh, okay, yeah. It's just because they're not symmetric. Okay. So let's create our polygons here that are missing. Cool. Yeah, we could actually increase here a little bit. So we give it some slack. And so we have our... Oops, no, it's not good. More space here, more space here, yeah. That's all right. And those reliefs, I'm gonna set them properly afterwards, their dimensions. I don't need them to be so big, and like the relief, the connection itself could be larger. This one. And here I can basically make this, and it's gonna respect the clearance. Now I grab here and I say polygon actions, report all. Okay, all right. So let's go here on the top now. I think those resistors are one part of the only things that are not gonna be symmetrical in the board. Oh my gosh. I mean, let's move this. This could be like 20. Nope, more. If you do show 30. Yeah, 30. This position, it's not gonna bother. No, rabbit the fiducia, yeah. Yeah, and let's do the same with the other one. 30. And let's just lock it in the place as well. Okay, good position. You want the fiducials like as most in the edge as possible of the board, because then you have the most precision on the pick in place. Because yeah, when you have them very close, your like angulation compensation, like you have more error. As larger the distance, the better. Okay, so then we can do like so, remembering that those traces are just temporary, but yeah, I also want to give some slack here so I can actually work. Yeah, and this kind of situation I don't like as well. So yeah, probably I'm gonna create a polygon plane connecting this, but only when I have the capacitors. I'm gonna have at least 4 capacitors. Yeah, on this side, like 4 big capacitors for the different rails. And yeah, on this side I'm gonna have smaller capacitors as well for the 15 volts that comes from this side. But that this is thought for other time. I'm not gonna immediately manufacture this board. It's go through review, but yeah, it's like 90% done in terms of schematic. Anyways, let's come back here. So let me see the position that I chose for the. So we select -13 for the distance. So let's define this one also as minus. Wait, no, I got the wrong measure, I guess. Minus 26.5. That is correct. Yeah. Oops. Minus 26.5. And this should be 0 because, and we also can do the same with the other. So on this case, can I make this, or is gonna just complicate it? Yeah, it's fine. So we can define here like 0 and here 26, not minus 26.5, and then we lock this guy as well, and those traces, they don't need to be that big. 0.6, yeah, more than enough. The same thing here. 0.6, go in the middle. It's all right. And here 0.8. What this trace does? This one is connected with this one. Interesting. Yeah, so this is a power line actually. So yeah, I'm gonna need you to think what I'm gonna do about this. Oh, actually I have plenty of space. Yeah, I can change this. Because I can go here, remembering that like power comes first. Then small signal on this case. Let me just polygon actions, report all. Okay, so it's alright, so I can create another polygon here. First, I wanna come here and do like so. And since we are already adjusting those diodes, I already wanna come up here on and say minus 26.5. This diode is actually gonna be like so, and the position, let's check his biggie. So it's 13. So 13, and we lock it. And we also come here and Let's say no. This is plenty. Like so. And we do the same on the other side. And it's gonna be like so. This label comes here. It was 13, 26. Lucky this one as well. All right. Almost there. There's no way to make those resistors pre. I'm just gonna make at least so align them. Align vertical centers with this guy. Why didn't you align this guy, please? Oh, why? Do I need to select that one as well? Ah, yeah, it's true. So if yeah, but it's already locked, so never mind. But then I can say you align with you, and I can say align horizontal centers with you, and you align horizontal centers with you. No, it's not grabbing. I hate when Altium doesn't comply. Yeah, I'm also suffering here because I could come here and say I want to migrate like so, and it would just work. This is a feedback line that doesn't really have a lot of, there's no power involved here. Okay. Okay, alright. Ah, just create. This way. It's so easy. It's so easy, Altium. Yeah, this way. Now we have a proper between pins routing. Ah, no. Now I need to define my grid very small. Yeah, that is good enough for Australia. All right, so hmm, it needs to go here. I was thinking, oh, maybe I can place like so, then I can move the signal here, but no, because I need to keep it that side. We have 3 warriors that are watching of all those hours, like 2.5 hours. Thank you very much, guys, for you that are since the beginning. I know that probably is very boring. Hey, but if you are here, I really appreciate that. Now I'm thinking which is the best position to go with. I think this is the best position. Let me think about it and place my wait, here I have the power plane, so okay, that is okay. So let's grab like a roundy, like 8 by 35, and this is gonna be like minus 8 by 35. So let's commit with this position, and then we can think about changing it if we judge it necessary. And since we are here, we can define this as 35 as well, and could be 24. Yeah, 24. So this one is gonna be minus 34 and 35, right? I guess so. Let's look how it's looking like right now. Yeah, very little to go. Very little. No, I don't know. I don't know if this is the right expression, but it's what we have for today. Now, oh, that's elegant. You have to say. Would be better if they were exactly in the middle of this line, but yeah. Okay, so now we are going to that moment that I need to start thinking about my power planes. I think I'm gonna start creating a so my brown layer, my top, I think I'm gonna have yeah. I'm gonna have my first, just let me break those errors here, because they're just bothering me. And especially while I'm creating planes, I don't like DRC errors. Reset error markers. Now, so what we're gonna do is come here, and we don't need to care, just because, yeah, Altium is gonna take care for us. And we're gonna see J and T. And of course, it's not gonna work because it never works. Polygon actions, report all. And now we have a perfect fillet polygon connecting all our grounds. Yeah, and here I'm gonna create a keep out region for our polygon, because yeah, we don't wanna high voltage on this region. So yeah, we need to create a, I think I'm gonna need to create a custom rule. Yeah, so what I'm gonna actually do here is just do a small trick. Let's say no. Yeah, like so. Then I can come up and say, oh no, no, it's not gonna work. So let's delete this and start over. I forgot about this. Okay, so from our low voltage, I don't care anymore. Actually, I just need to have the here. And yeah, so from here, I also don't wanna bring it closer to the output. So I'm gonna do, yeah, like actually this doesn't matter, because yeah, here I'm far enough from the pads, and here is low voltage, so this is not an issue. And let's bring like so. I'm gonna do some optimizations afterwards. For example, we don't need all this clearance here, so we can say here is good enough. We can also say like here is good enough. Here is the same thing. You can bring this closer. And let's bring this a little bit closer, and this one a little bit closer, and this line like so, and this also like so. Yeah, it's enough clearance for what we need. And yeah, I should have done what I did here. It's alright. Report all. Okay. Yeah, actually I have, yeah, no, let's keep it this way for now. Okay, so yeah. There's a good isolation between we have the pre-pack, but we have only 0.2 millimeters of pre-pack. I'm gonna need to check afterwards how many volts we have of isolation between the pre-pack. Yeah, because our core material is between the inner layers, because yeah, we start with a double side PCB. So most of our core is there, our biggest isolation, and then we have like 2 layers of pre-pack that are 0.2 millimeters of isolation material, is basically epoxy, and then we have the deposition of the outer copper layers. So yeah, I'm gonna need to check on the specs since I'm like basically placing this plane here. And actually I think I'm gonna stick with, yeah, I'm not comfortable, not gonna even change. I'm gonna come up here and I'm gonna say layer 2, because now I'm totally safe, and I can come here and say polygon actions, report all, because I know 100% sure that this this layer has enough isolation, because then we have a pre-pack layer and then we have a core material of isolation. So we should be fine now. And so on this case, now those oh, this blue is just burning my eyes. Yeah, I'm gonna hide the layer 3. Yeah, it was just burning. It's too bright. Yeah, so now we can wrote those components that I'm just procrastinating a little bit to wrote these capacitors and resistors, but they are very straightforward. Okay, so HV, high voltage. So we have the HV bus on this side. So let's see where they going. So they go here. This goes there. So this one needs to turn like so. This one goes there. And this one goes like so. So based on what I see now, I think we can create like a nice straight line for those components. I think I'm gonna start just like aligning this resistor like so. And I see that this one has the same responsibility in this one. Yeah, so this guy could go here. Oh, okay, so this is that connection that we must go, and then we do on the layer 1. And this one we can basically do the same. We bring to its pair. this is the way. Yeah, and now we can use that nice Altium alignment and thing and say distribute vertically. Yes. Yeah. So what happens is this is more convention. The layer 1, usually you only use it for the board outline, and the mechanical 13 is kind of general purpose. So yeah, this is more or less the convention that you have. Like the mechanical 13, the manufacturer basically is not gonna care about what you have that layer. So yeah, so like as you can see here, I have like the board outline. It is on the mechanical 1. And those components, I think they are generated with the mechanical 1. But if it was me, I would be generating on the mechanical 13. But yeah, like the mechanical layers, the only thing that the manufacturers cares about is the outline. What is inside, like, because for the cutout you have specific. I don't know where the cutout actually goes. Maybe it's in the, no, I don't remember. It's the 15. Yeah, but there's a specific layers for a specific layer for the cutout. I don't know if Autumn generates separately. Yeah, so, but yeah, that is what I do. I keep like general purpose mechanical things like on the 13, and mechanical 1 I use for outline. Okay, so now you see that we have a proper spacing here. And we can route the signals. And here I'm gonna put like 0.8. Oh no, because so 6. Yeah, this is kinda not necessary, and this one I can just change a little bit. So 0.7, I guess, gonna give me enough clearance. Yeah, like so. Just to keep some nice and straight trace. I could contour. I could just contour, the component. But yeah, since we are here, like so, like so, like so, just boring tracing right now. Yeah, it's good enough. As Dave likes to say, it's good enough for Australia. And yeah, so for now we connect here. No! No, Altium. Now is not the good moment for you to do this. No. Yeah, it's the rod is not properly connected here, as you can see. So it thinks, no, you're not connected. Now it should not delete it. If you delete it, yeah. Now Auto understands that we have a connection, so it's not gonna take decisions for ourselves. I just, oh, no. This is this all right? No, but actually I'm forgetting things. I'm forgetting that I must connect. Yeah, we're gonna need to make some changes here, because I have my medium voltage rail that must be connected. And the thing is, like, if we come up and say, oh, we need actually more copper, we need, for example, 2 ounces because we want to handle more current. It's easier, usually it's simpler and cheaper if you do in the out layers. So when you have power trays, always keep them in the top and bottom, because it's just a more straightforward to the manufacturers to keep like one half an ounce or 1 ounce in the middle, and then you can have like a 2 ounces in the top. It's less manufacturing process, so it just end up being cheaper. So on this case, I just realized, oh no, I actually can't have this because I need space. So this resistor is gonna need to come a little bit closer, like so. So for now I can keep like yeah, so that's the moment that this my phone is ringing. Yeah, so we're gonna bring them like so, same space now, a little bit more. So you come here, you come here, and then we have plenty of space to say, oh, come here, and let's connect it like so. Hey, and then we wrote those irrelevant signals. Not irrelevant, but yeah, you get me. Under our layer 1. And it's actually very convenient because we already have another signal here that needs to come from the layer 1. So now is that moment that we start thinking about vias, and it's gonna be very convenient because we can actually do this. And this is one of the points that we wanted to, nope. Yeah, there. To create our vias outside, because we don't wanna bring or solder inside the via. Yeah, so now I'm gonna need to report my polygons because yeah, we have a ground. Yeah, so now I needed to take care because I'm gonna have our thermal vias there, so and just yeah, that is perfect. Yeah, it's better to bring here for the middle, and you're gonna understand afterwards what I'm doing here. But yeah, G. Yeah, better. Since the feedback here, it tracks very closely with this line, I don't have an issue with interference because yeah, we already have a resistor and a capacitor here. So it's not an issue whatsoever. This is the only reason that I'm basically tracing those lines under here are outputs. Otherwise I would never do this. Here. That's all right. So now we can say come here, and yeah, this is the way. can do basically the same. Like so, and now we can do the same. Yeah, just keep here for now because we are still working on this side. And here, since let's go to our top overlay to grab this guy, bring it here so we can have some consistency between our, yeah. And since I brought, interesting. You see here a pattern. So here I put the capacitor in the middle, and here I'm gonna move and put the capacitor in the middle as well, because, and I also gonna move the distance. Okay, I know more or less the distance that I had there, so I'm gonna basically put the same distance here. And this trace can go like so. Yeah, and now we have a happy. And we place our via. This is a big via. We don't need a via so big, but space we have plenty. This is we're gonna fix afterwards, probably with a whole polygon here. Yeah, I just wanna get this done because we are like in 3 hours, in 8, 9. Hey, 3 hours. Yeah, so I'm getting tired, and it's like already like 8 in the evening in Germany. So let's finish this puppy soon. All right. And here on this case, I have a little bit more space. So you can bring like so. And now, yeah, so here, because it's okay, because my components are inverted. When you're planning on getting this board fabricated, probably, well, if everything goes all right, this week until the end of the week, should be going for fabrication. I have a few boards to fabricate, so maybe I'm gonna join different orders, because in the end, the freight is more expensive than the boards nowadays. So I have some front planes that I must do. Yeah, so I think I'm gonna send a batch of boards, but yeah, first I need to finish their design. So, and I'm not exactly in a hurry to send this specifically board. So as soon at least I'm gonna share the schematic. So if like Marco or Kat wants to fabricate it, the board's ready and they can like starting assembling their own. And since this is like is the board for the Ericsson SMU, if someone wants to build the Ericsson SMU already with our new amplifier, they already have it as well. So yeah, so this is the idea. G. Okay, so let me see how far I put this. 31.5 millimeters. So this one is gonna be 31.5 as well. Here. Oh, absolutely. When I get mine, we're gonna be soldering this board together. I'm gonna place it in a hot plate, and we're gonna populate the components and see it melting. Absolutely. Yeah, we do another live stream. It's gonna be cool. Uh, okay, so R4 is our next candidate. And oh wait, I put see-through. Yeah, I put the capacitor in the middle, so we're gonna respect. Did we kept? Okay, so we kept. I see that 3 hours is kind of my limit of live streaming. My brain's like already starting to hurt. I'm really not used with this. Usually when I am working, I take like breaks, but since I am with you guys, I can't. So okay, so now we're gonna put another via here. And our net is connected, and we can come to the polygons and report the violating polygons. And for the sake of symmetry, I should probably bring this like so. Yeah, and this one actually can come on. Yeah, like so. Oh, gorgeous. What do you guys think? Are you happy? Let's give you some context. Yeah. Yeah. No, I'm not. I am actually a software. Currently, I am a software security engineer. So that's it. But yeah, I worked for, as a software engineer for a long time, but now I'm more like in the security engineer part of things. Okay, so this. Electronics is just a hobby for me. Despite the fact that I can sound a professional, this is not my daily job. Oh yeah, like electronics to me is like something that I always enjoyed, and I like to keep an eye on always. So I don't think I want this capacitive coupling right now here. Yeah, let's bring it to the middle so we can have a slice of symmetry on this unworthy unsymmetrical triad of resistors. Yeah, like I already like worked like indirectly with electronics, and I had like one official working experience when I was actually developing hardware. So many years ago, this was in 2011. Yeah, so I worked for a LED panel company, and so they were like LED panels manufacturer, and we on that moment we just had like monochromatic panels, and the company wanted to develop RGB, full color LED panels. So I worked on a driver, a video driver that would communicate with USB, and then we had like interface that would convert from this USB to a like a raw RGB using like differential pairs like RS485, what we used in that moment, like many lines like for each one of the colors, and yeah, and distribute to the panels. So that this is like the only official like as an employee experience. But I also do some consultancy job. So, for example, now I have a customer where we are working on a project. Is more like in the embedded side of things, but yeah, we are doing part of like microcontroller firmware development. So I have a like a side business as well where I do some consultancy. but it's just like it's really a side hustle. Anyways, okay, so now here, as you can see, we have those traces that they cross, and since we used, okay, so here is where I actually gonna change my mind, and I'm gonna move this feedback line to the bottom. Do I have anything else here? Yeah. So now I have a good reason to do, oops, and now I can actually make this over because I have like shoot. Yeah, and I can do mechanical design as well. But not, let's not get too cocky. Okay, let's put a via here, because yeah, when we can hide vias because they are ugly. So it's harder and softer, yeah, exactly. Absolutely. And we're gonna bring, yeah, let's bring this via inside here, and this via also inside. All right, now we repour. Oops, wrong layer. So now we go to our layer, call it layer 1. And you can see that we have a good symmetry as well here. And we only have those so now we can do like so, and also the same thing here, like so. Then we do oops, I put on the wrong. Is it correct? Yeah, so this is, okay, because this is connected here. Okay, so we have one more via. Just curious, why quad CPI for the ADC? Because the ADC has 4 channels. So with the if you check on the ADC communication mode, it has a mode that using quad CPI, you send each one of the channel data in each one of the data channel. So you don't need to I received the channel 1, then I received the channel 2, 3, and 4. No, you receive the 4 channels at the same time, you know, in each one of the data lines. So yeah, it keeps like way tighter and way faster to receive our samples. Ah, it's so close. Only a few resistors. That's it. And there you have it, guys. There are a few details yet, so I'm gonna need to convert some of those traces um, to power planes now, but honestly, I'm tired. So this is our, well, there's a lot. Like I have to create yet here on the bottom layer. As you can see, our bottom layer was not used because now I'm gonna create like polygons here, and those polygons are basically gonna be our heat pipes from the transistor pads, and so I'm gonna spread them, and their only function is to sink the heat from the transistors to the heat sink. So I need to do six polygons, one for each one of our power transistors, and that's it. And here in the top, I'm gonna create then the capacitor components that are missing, and place them on these regions here. Also, I'm gonna place more like 2 capacitors here, small ones for the 15 volts line as well. So some filtering capacitors there. And yeah, that's pretty much it. I think there's a big chance that I'm not gonna use electrolytic capacitors. And the reason for that is I don't wanna increase too much the height on this board here, because the idea is to stack amplifiers, and every like single millimeter that I lose here is more like space that I need in the enclosure. So for this region, I'm gonna probably only use like tantalum capacitors or using multi-layer capacitors. So I can have like the slim layout as possible on this board. So that's it for tonight, guys. I finished the routing. I know that I'm cheating a little bit. It's missing power planes, but I'm just tired now. And after like almost 3.5 hours, I think I reached my limit. So I appreciate for you three viewers that stayed here until the end of this live stream, and I see you the next